my name is Amador Terán Gilmore. I work at Universidad Autónoma Metropolitana in Mexico City, and I will be talking about disaster resilience, particularly from the perspective of earthquake-resistant structural engineering. Just as a background, I would like to mention that the type of structural systems that we build today were born at the end of the 19th century, the beginning of the 20th century, with the birth of modern architecture. We need to admit that there was a lot of decades in which we really didn't understand how to provide safety and efficiency to our structural systems. But about the mid-20th century, we start understanding what is important for efficient and safe structural design in terms of earthquake resistance. And all those things that we learned have brought us to today, in which I can say that we can achieve in the real world a resilient-based design. In all this evolution, our design formats have gone from a rather simple format at the beginning to the refinement that we see today. And some of the ideas and the things that we initially thought that we should be doing have evolved until to the situation that we feel it's the best, to the type of things that we currently believe we need to be doing and that we should be doing in the future. So I'm gonna concentrate my attention to a big change in which we feel that we should be abandoning the force-based design format and making more emphasis, not in strength, but on stability and control, and that implies moving into a displacement-based format. What's the sense of purpose of all this? To proactively contribute to improve post-earthquake outcomes according to the needs of modern human societies. Particularly, we don't want all natural phenomena to become natural disasters. So we have paid a lot of attention to understand why buildings develop damage during earthquakes, because damage translates to losses. And this is kind of complicated because a lot of things get damaged inside our buildings during an earthquake, and losses can be expressed or computed in many different ways. But one thing we can say for certain, that excessive damage is what is leading us today to the unwanted outcomes that we have every time we are subjected, or our built environment is subjected to intense ground motions. So we have carried out a lot of research in experimental, analytical, and the field. We have integrated all this research, and we finally have achieved some understanding of why our structural systems and everything that is inside them get damaged during earthquakes. We usually use plots like this, in which in the x-axis, we plot the lateral deformation of our structural systems. And what we have learned is that structural damage and non-structural damage is a consequences of lateral deformation. The larger the lateral deformation, the larger the level of damage. And we have tried to establish what we call performance levels that describes us in words the consequences of the damage. So in qualitative terms, immediate occupancy is a level of damage that allows for a structural system to be occupied immediately after an earthquake. Although life safety implies a larger level of damage, we can guarantee the safety of the people that occupy the structure. And collapse prevention implies much more damage, but we don't lose the structure does not lose the capability of carrying its gravitational loads. So if we keep the structural system within its elastic range of behavior, we have very small damage, and we can guarantee then the immediate occupancy. Once we go into the nonlinear range of behavior, damage starts increasing fast with the formation of the structural system. So depending on the different structural types of elements, we do a lot of experimental testing and associate displacement ranges for these different performance levels. And there's a sense of purpose to this. We establish performance levels that make sense in terms of outcome in such a way that we can relate the engineering we do with the outcome of the earthquakes in the field. There's not only structural members in our structures, there's also contents and installations that are very valuable and they are important too. But just for time limitations, I'm just going to address the structural part of the problem of controlling damage in terms of the structural systems. So our current approach to earthquake resistant design, as we mentioned in one of the first slides, is based on a strength-based format. One important concern of us when we use this format is stability, the stability of the structural system. What do I mean by stability? It is very important that our structural system is able to develop its full lateral strength. But it is as important that once it reaches its maximum strength, it is able to sustain that strength, to maintain that strength for large displacements. That's what I'm calling stability, the capability of a structural system to keep its strength for large deformations. And to explain why this is so important, I will give you the case of a paper clip. If I want to break the clip, I cannot do it even if I apply to it large deformations. So in a sense, we want our structures to behave like paper clips during intense ground motions, that they would deform, but without failure. To achieve the required level of overall stability, earthquake-resistant structural systems need to exhibit three properties. What I call local stability, which requires adequate design and detailing of each structural element. And why do we are very careful in the design and detailing of each structural element? Just to avoid the type of performance or behavior that I'm illustrating with this picture. Also, our structures need structural integrity, which requires adequate design and detailing of each connection. And why do we need to be so careful in the design and detailing of every single individual connection? To avoid this type of behaviors, in which we can see structures in which the structural members or elements exhibit very little damage, but there is a collapse because of excessive damage in the connections. And also in terms of structural integrity, we are paying a lot of attention in the design and detailing of the floor systems, because somehow the floor systems interconnect all the vertical elements of our structural system and makes them work together. A final property or quality that our structural system needs to have is structural regularity, which requires fairly simple structural systems that do not concentrate its nonlinear behavior in an excessive manner. If this happens, at rather low global lateral displacements, all the nonlinear deformation is concentrated in a few elements, and that results in excessive local deformation. What that means is that at low to moderate low global lateral displacements, there's very heavy damage in a few structural systems, and these results that at this low level of deformation, the structural stability is compromised. And that goes far from what we're trying to do, which is provide stability to the structural system. So the strength-based format initially focused on the strength of the individual structural elements, but later was complemented with drift control and complementary design detailing requirements. So at first, we believed that strength was the most important property that a structural system should have, but then we understand that we needed to provide stability. And we also understand that stability just does not happen. It needs to be conceived, designed, and built. In parallel to the understanding of the importance of stability, we in parallel understood that we needed to control the lateral deformation of the structural system. So we decided to control the lateral deformation as to achieve life safety. Notice that this implies significant damage. But this type of performance was expected for what we call the design basis earthquake, which is a small probability event. And it is a very small probability that will occur during the lifetime of the structural system. And why do we accept this significant level of damage? Because of money. We thought that trying to control the lateral deformation of the structural system to smaller values to achieve less damage was too expensive. And given this small probability, it makes sense to us at that point that we should allow for these large deformations within the force-based format. And although the strength or force-based format has been very useful in terms of improving the performance of earthquake-resistant structural systems, it is currently preventing us from using the state-of-the-art in earthquake-resistant design to improve actual seismic outcomes. What are the main limitations of the force-based format? Well, its main limitations are a consequence of the inconsistency that arises from using an elastic analysis to estimate the seismic response of a system that is designed to develop significant nonlinear behavior during the design basis earthquake. See, elastic analysis to estimate nonlinear response or nonlinear behavior. Although specific checks are included so that the lateral response of the structural system is controlled within prescribed drift limits, the expected level of seismic damage is not evaluated and the demand-supply balance of the formation is not verified. As a result, the expected performance cannot be assessed. Remember that the outcomes that we are having after earthquakes are consequence of damage, and this format is not verifying the actual damage that is expected in the structural system. What this is resulting in is in a divorce between design decision and consequences, because the engineer cannot understand how to improve the performance of the structure if he doesn't understand what's the level of damage in that structural system. So this is taking us very far from proactively contributing to a desired outcome. So what are the implications of using this force-based design? Here is losses in terms of US dollars, billions of US dollars worldwide. And we're going from the year 1900 to the year 2010. And independently, if we live in a developing country such as Mexico or in a developed country such as Japan, we can see that the level of monetary losses are increasing exponentially. And that begs the question, if these exceptional intense ground motions that we were feeling that will not occur, has the exception, in those terms, has the exception become the norm? And we can say that we're achieving adequate structural safety, but at what cost? The facts are, first, our design basis earthquakes are not as exceptional as we once thought. And second, we are using expensive and inefficient structural systems that end up having varying structural safety margins and are prone to damage. So when you discuss this with the public, when you explain, you try to contextualize all this to the public, what we are understanding is that people are not expecting that life safety performance. What the majority of people feel that within the actual circumstances, we should be aiming at higher performance levels, such as immediate occupancy, or even like having fully operational structural systems after intense ground motions. So clearly, there's an imbalance between what we believe in the past and the level of loss and the social expectations of what a structural system, an earthquake-resistant structural system should be achieving today. That brings us to resilience-based design. In terms of the design basis earthquake, we're still okay with achieving improved stability at larger displacements. We can achieve this at a reasonable cost. We already talked about all what we need to take care of to make possible this improved stability. But what we are now focusing a lot of our attention is on improving the performance of our structural systems. Why? To reduce losses. And what we're proposing is to reduce considerably the lateral deformation that we're allowing during the design basis earthquake, from the life safety type of deformation to a much reduced one that is associated to immediate occupancy. And there's a lot of initiatives that are helping us understand how to achieve in an efficient manner this reduction of the lateral deformation in structural systems. For instance, the READY rating systems, which stands for Resilience-Based Earthquake Design Initiative for the Next Generation of Buildings. It is clear for us that to achieve this reduction, we need to change from a force-based design to a displacement-based design, because we need to understand how design decisions affect performance or consequences in our structural system. As displacement is correlated to damage and damage is correlated to losses, then we can establish that connection. And besides that, we need to go beyond a myth that we have that providing this lateral displacement control is very expensive, because currently it is not. I'm addressing two paragraphs that I took from the READY, in which I want to outline to you that it says here that it is now possible to achieve far greater resilience at minimal additional investment. This is not a problem of cost or money. Also, we need to understand that long-term planning is the key to achieving a truly resilient facility. So a lot of people are asking, do you really think that we can establish a new sense of purpose for earthquake-resistant design? And yes, what I'm saying is, not only a lot of people are saying that new knowledge makes possible a new sense of purpose. And we need to really be aware that we're currently using a design approach that was established in the mid-20th century. And basically, if we keep doing what we're doing, we're ignoring 60 to 70 years of learning, research, and technological development. That's why we can understand now this slide, why to achieve a resilience-based design, we need to make emphasis on stability and control, and we need to change from force-based formats to displacement-based formats. The evolution of earthquake-resistant structural systems speaks for itself in terms of what architects and engineers should aim at in high seismicity zone, because we clearly see that through that evolution that we have tried every single time to improve the lateral displacement control and to improve on the structural stability. So this is the type of systems that we have at the beginning of the 20th century, didn't have sufficient displacement control. So we start moving to heavier frames, but this was very expensive and inefficient. Eventually, we start supplying our structural systems with braces and walls that are much more efficient at controlling the lateral deformation. And somehow we're in the new generation of structural systems, we're going somehow back to this lightweight. But understanding that these lightweight systems don't have lateral deformation capacities, we're supplementing them with control devices that with very little added weight can provide in a very efficient manner the lateral control needed by the structural systems. We're going even into the concept of integrated differentiation. And to explain this concept, you just think about a human being. It has a lot of independent systems, very specialized in developing just one function, but that are capable of integrating all that function to give a very functional and highly developed being. The same with our structural systems, where through integrated differentiation, we're starting to learn that the most efficient way to deal with our systems is to provide a system that exclusively carries the gravitational loads and a series of devices that specifically controls the lateral deformation of the structural system. We can achieve then very efficient structural system at low monetary cost and with the safety that is required from them. I would want to offer a series of final reflections. My point is that new knowledge and improved technologies allow for a new sense of purpose in earthquake resistant design. In terms of balancing the pros and cons of keep doing what we're doing today and moving towards a resilient structural systems, I say that when we consider the long term, it's clear that we should move to this resilient earthquake resistant design. When we value the losses in terms of money, in terms of the environment, and just in terms of the well-being of humans, it is clear that all the variables, all the parameters clearly indicate that we should be moving now from what we're currently doing to a resilient earthquake resistant design. Why currently this is not happening? So why are we still building so much more conventional systems as an alternative to resilient systems? Well, the question then is, what is preventing us from designing and constructing a better built environment in high seismicity zones? Well, I surely acknowledge that we live in a complex world, and that will always be reflected in huge multidimensional challenges, conflicting interests, conflicting opinions, conflicting ideas, and that it's a multidimensional world. I get that. But I still believe that at this point, we could and should have done a little bit more. And two things I know from the experiences I have had in Mexico. That first, we're slowly moving in the right direction. And second, that college education will be one of the keys to achieve a resilient built environment. I can tell you that whatever we have achieved in terms of resilient design in Mexico has been through the talent, the compromise, the enthusiasm of some generation of Mexican students that have been trained in Mexican universities, and in which education, all these type of concepts were included in their education, so that they have the motivation to change the world in a better way.